Yeah. So we know from unit number 3, we have studied about what is known as a bistable element. Okay? So these two inverters, when they are connected in a positive feedback, they form a bistable element. Okay? So this means that if I have a node Q, if this is at logic value 0 or 0 volt, then the other end of the node will be at 1.2, right? So now, in order to modify or any data which is available inside this bistable element, we need these two transistors A1 and A2, which acts as access transistors. Okay. So now the other end of the access transistor nodes are being connected to the bit line and bit line bar. Okay. So So now, in general, this SRAM design, or basically the SRAM operates at two different phases. In the first phase, which is called as a pre-charging phase, the bit and bit bar lines are being pre-charged to VDD. Okay? While the other phase, which we use either to read as well as to write any data onto this, okay? So onto this SRAM cell. Okay? Yeah. So now the way that we are going to distinguish between these two phases is because by mapping this word line or WL to equal to 0. So when this word line is at logic value 0, then we actually have this bit line and bit line bar to be charged to VDDs. Okay? But then when I switch to VDD or 1.2 volt, then we can perform either read or write based on whether we are driving the bit line or not. Okay? So first we'll just begin with the read operation. And before that, let us try to have some initial condition when I am at pre-charging phase. Okay. So now during this pre-charging phase, that is when the word line is at logic value 0, we have this 1.2 volt and 1.2 volt on both the bit and bit bar lines. And we will also assume that the node Q is at logic value 0, while the other end of the node is at 1.2 volt. Okay. So now we are going to perform a read operation, but before that, based on this initial condition, let us try to see which are the transistors that are on. Now, as we could able to see that the node Q actually drives the second inverter, which is formed by P2 and P2. Now, what will be the, like among these two transistors, which transistor is on and which transistor is off? When I have this Q is at logic value 0, that is trying to drive the gates of P2 as well as P2. Now, which one would be on in this case? P2 is on. Yeah, so P2 is on while this guy is off. Now, similarly, and you could see that my Q bar is driving the first inverter gate terminals, right? So, again, in this case, it is this P1 that is on while the P1 is off. Okay. Now, let us try to switch to VDD, and we are going to perform a read operation. Okay. So, this means right now my A1 as well as the A2 transistor is on just because the gate is connected to the supply voltage, which is 1.2, right? Yeah. So now I have two structures in the first branch and two structures or two transistors in the second branch. So let me list them out. This is A1 and B1. Okay. While we also have A2 and P2. Okay. So among these two transistors, these two set of transistors, which one do you think that performs some sort of read operation or some sort of charging or discharging can happen across which branch among these two structures? So let us go with this A2. I have 1.2 and 1.2. Does it involve in any sort of charge transport across this A2 transistor? No. So obviously this is not going to get involved in any type of charge transportation or any type of current flow. Okay. So what is left over is only this A1 and B1 structure. Now let us try to see and understand how does the structure will behave. So I will take these two transistors separately. And now because this bit line are being charged, which means these bit lines are so long that they have some parasitic capacitances, and this capacitance is basically modeled by a capacitor from an analog lid. Okay. So we have these capacitors here. And I'm just going to model this parasitic capacitance with that capacitor, which is taken from the analog. Okay. And I have this transistor A1, while the A1 gate terminal is connected to VDD. I just connected here, and we could be able to have an NMOS structure, and the input of this gate is again connected to VDD, which is 1.2. So I have this structure. Okay. So right now this is at 1.2 volt, and we also have one more node which we label it as Q. Okay. So according to this condition, initial condition, what I have is the node value which is equal to 0. Okay. And when these transistors are on, we know that each of the transistors will have some on resistance. And let me model this on resistance by RA and RD, and I have one capacitor that is being charged to 1.2 volt. Okay. Now what could happen to this Q, the node voltage at Q? Will it stay at 0 or will it change based on the condition that I have placed here? It will change. The reason is that there is a current that has to form a loop, and because of that, this will change. Now, if at all, if I assume that the value of this RA is equal to RB, what is the maximum voltage that it switches? So, why only one is speaking while what happened to the others? What is this resistor forming across this supply of 1.2? It's a voltage division rule, right? So obviously, based on the voltage division rule, if I assume that there is a change in the voltage, which I monitor as delta V, then I can write it as RD divided by RA plus RD into the supply that I have here across the input of this one. Okay. Now, under the assumption that when both the resistors are equal, what happens is that this voltage will be close to 0.6 volt. Okay. So this means from 0, it will have a bump, and this bump will reach a maximum value of 0.6. Okay. But then after that, it will also get reduced back to 0. Now, why is this reduction of 0 is happening here?
Because it's a capacitor.
Yeah, because it's a capacitor, it's not a fixed potential that I'm trying to fix here. So because of this capacitance, the capacitor will try to lose its charge as the current flows through this particular loop. Okay, and due to which, even though I mentioned that this particular voltage will go all the way to 0.6, it never goes actually. So some sort of voltage will happen here, and we will try to reach this maximum. Okay. So now, I want to look at the voltage transfer characteristic graph of this inverter. Okay. So what I do is I will just come back here, and I will try to plot the VDC graph of the second inverter. Okay. So I'm going to talk about the second inverter VDC graph. Okay. So now what is happening is that the Q node is changing or varying from 0 to a maximum. Let us assume that it is going all the way to 0.6. And due to this, let us see what is happening across the input to the second inverter and across the output as well. Okay. So let us assume that this inverter has an unskewed inverter, which means it will have a switching voltage Vm that is equal to 0.6, and it can be swept from 0 to 1.2 in this range, and due to which the output will also react something like this. Now, if this voltage is reaching all the way to 0.6, what is happening is that from 0 input voltage, this is my input axis, and I will try to create a bump, and this bump is going all the way to 0.6. Now, what does it in turn gives us back? The output voltage of the second inverter is actually getting disturbed and pulled all the way to 0.6. Am I right? From the voltage transfer characteristic graph, when I make a change or when I try to create a bump across this Q node, because of this peak value of 0.6, what is happening is that this is being applied to the input of the second inverter. Okay? So this is being applied to the input of the second inverter, and we are trying to analyze it. Okay? So when the input is at 0, my output is at 1.2. Okay? So the output is at 1.2. But then when I reach to the maximum value, the input goes all the way to 0.6, and due to which what I have across the output is also getting modified. Is this operation is fine or not?
No.
While reading, I should never disturb the data that is being stored here. But because of this, what is happening is that I'm trying to disturb the value that I have stored across this Q bar, okay, which is being pulled from 1.2 to 0.6, which means this particular loop can lead to what is known as a metastable state, which you might have already studied in your unit number 3, which I will not go in detail here. So now this, I want to get rid of this. So what I can do is, instead of having this particular bump going or reaching all the way to 0.6, rather I will try to reduce this bump height by a certain amount. Okay, so now for this amount, I have to ensure that this bump, that small bump that I'm trying to create, should not disturb the value across the output of the second inverter. Which means this bump, which is being fed at the input side, should ensure that it doesn't change this value much. Okay, so due to which, our goal is to make sure that the bump can go all the way to 10% of your VDD, which is nothing but 120 millivolts. So this is the maximum value that I'm supposed to have, so that I'm not disturbing the output of the second inverter, moving away from this 1.2. Is that fine?
Yes.
Any doubt till now? Okay. So now to perform this, how do I ensure that this bump is not reaching 0.6, but rather I want to fix to 150. So what is the idea behind this particular value being reduced? How do I reduce this value of the bump to 120 millivolt? I have this formula. What am I supposed to do across this formula so that instead of getting 0.6, I want to make it as
Reduce
RD.
okay, yeah. So the best way is to reduce the value of this RD. So due to which the total ratio will end up having a value of 120 millivolt. Okay. So if I want to reduce the value of RD, okay, what am I supposed to do with respect to the width of the transistor? So resistance is inversely proportional to the width, which means if I want to reduce the value of this resistance, I have to increase the value of the width of the transistor. Okay. So now during the simulation, you are going to have this width defined as WA, while this width will be defined as CR times WA. Is that clear? Now, in this case, what is important for us is to find the value of this ratio, okay, the cell ratio, so that I end up having this as my bump that is being created in our simulation. Is that clear? So, in turn, we are going to try to have a parametric analysis trying to speak the value of this CR, and we will find a particular value of CR that satisfies our requirement of the bump having a value of 130 millivolt. Is it clear?
Yes.
Yeah. So now we'll just move on to the next one where we are going to perform a write operation. Okay. Now the write operation is a bit trickier to understand and also to explain. I'll try my maximum best to explain this. Okay. So when I am at initial condition, which means when I'm performing the pre-charging phase, we know that each of these big lines will be charged to 1.2 and 1.2, and I have some set of capacitor, and the internal node voltages are equal to 0 and 1.2. Okay, so this is what the setup is all about. Now I just want to write some data so that in the place of Q that is equal to 0, I want to change to 1.2, while this Q bar, which is the node potential here, I want to change it to 0, which means I have to ensure that this driving force has to be forced through this bit and bit bar line, which also means that we need some sort of driver circuit. Okay? And this driver will have some width, okay? And I need to apply some data across this. Okay? So how is this data supposed to be applied to the gates of this driver? So say for example, if my DN is equal to, when I apply my DN here as a gate input for the bit line, what is the label that I need to substitute here to drive the driver of this bit line bar? Can I apply the same DN or it's supposed to be different? What is the meaning of this one? Bit and bit bar, or basically bit line and bit line bar? They are complementary in nature, which means even the data in that I am trying to force also supposed to be complementary in nature. Okay? So now because I just want to force a value of 1.2 here, this one needs to be at 1.2, which also means if my data in is equal to 0, then this turns is off and the pre-charging voltage that I have will be retained as it is, while on the other end, I'll be forced to have a logic value 1 across this gate of this driver, okay, which is 1.2 volt, and that will ensure that this node is connected towards the ground. Okay, that is all clear? Yeah. So now, again, I have some set of transistors which I supposed to discuss. I have this A1 and D1 for the initial input condition while the word line is at 0. So I have this A1 and D1, and also there is a combination of A2 with P2, right? Now, which among these two combinations will help us to perform the right operation? I want you to think and then let me know. Shall we go with the first one? Let's give it a try and see whether it fails or whether it tries to prove that it can be used for writing operation. So now in this case, I have this 1.2 volt and I have a 0, and then I have this logic which is connected. Okay, so I'll use the same setup as before, and this is my D1, this is my A1, and I have this supply voltage which is around 1.2, and everything is connected right now. Okay, now what happens is that this voltage actually, due to the current flow, will actually change from 0, and what is the maximum value that we can attain after sizing for the read operation? What is the sizing that we have chosen so that this can go all the way to?
120.
So this can reach all the way to a maximum value of 130, because based on the sizing that we use for the read, I'm going to apply the same sizing here, and due to which the Q node, instead of changing from 0 to 1.2 volt, it can change only to 120 millivolt. It's just 10% of your supply. Okay. Now I'm going to use this one to drive the second inverter. Okay. So let's see whether this 120 will help us to invert the voltage across this node from 1.2 to 0. Okay. Will it happen? This is a bump that I have created from 0 volt. Okay. From 0 volt, I have created a bump, and this bump can have a maximum of 120 millivolt. Now, when I apply the same bump here, I have to ensure that the output is changed from 0 to, from 1.2 volt to 0. Does it really change when I apply this input? No, it doesn't change. Which means the combination of this A1 and D1 fails to perform a write. Okay. Now let us look at the combination of A2 and P2. Okay. So in this case, I'm just going to assume this VTC graph for the first inverter. Okay. So this VTC graph is with respect to inverter number 1, okay, which is the combination of P1 and D1. Okay. Now whichever of the transistors that are on is A2 and P2. So which means I have this P2 transistor, which is a PMOS, and that is being connected to a 0, right? So because I had a 0 here, and due to this I have been connected to the gate of my P2. So I model that as a ground here, and then I have this A2 transistor which is connected between Q bar and the bitline bar. Okay. And that's being connected to VDD, which is being modeled like this. Okay. So now the other end is basically a capacitor and a driver. So before I talk about this driver, I'll just model this as a ground here to mimic that this particular node is being pulled all the way to 0. Okay. So now I have this P2, A2, and now let us apply the same model. This, let us assume that it has a resistance of RP, and this has a resistance of RA, and it's being connected to the ground. Okay. Now, initially, we know that this value of Q bar is basically at 1.2. The moment I switch this word line from 0 to VDD or 1.2 volt, what happens to this Q or Q bar? What is this voltage? What change in voltage will have? And assume that I have this RP equals to RA. 0.6, right? So in this case, from 1.2, it goes all the way to 0.6. Okay? And this is acting as the input to the first inverter. This entire voltage swing that I am having is acting on the input of the first inverter. And if this is my first inverter, which means my previous input was 1.2, when I had this 1.2 as my input voltage, the output voltage of the first inverter or the node Q was at 0. But now I pull this node from 0 to 0.6. And assuming that this is an unskewed inverter, I have a switching voltage of 0.6, which means that the output voltage will be at 0.6. Okay, so rather than pushing this one to 1.2, I could able to barely push it to 0.6. Now, how will I push it further to into 1.2? Is my question is clear? If this node can switch from 1.2 to 0.6, and that has been applied to the input of the first inverter, the output is also switched from 0 to 1.6. Okay, but our intention is to ensure that this node is being pushed all the way to 1.2. How will I achieve this instead of stuck to 0.6? Is it difficult for me to?
Increasing resistance of RA.
Okay, so now the only thing is, if I could able to reduce from 1.2 to say for example 0.3, now for this 0.3, I have an output voltage that is close to 1.2. Okay, so now I want to drop from 1.2 to 0.3. How will I do that? Yes. So we know this voltage across this one, let me label it as delta V bar, okay, is defined as RA divided by RA plus RP into VDD. Correct? So now to reduce this one from 1.2 to 0.3, I have to reduce the value of this RA. So if I reduce, then obviously we can bring this, instead of switching from 1.2 to 0.6, I can make it to switch to 0.3. Okay? So in our case, we'll fix it to 0.3. Clear? So when I'm able to switch from 1.2 to 0.3, then I am in a safer zone so that I can pull this all the way to 1.2. Okay? So to be frank, while I'm performing this 0.3, the exact voltage, when you perform a VDC graph, it will not be exactly equal to 1.2, but rather it will be a value that is close to 1.2, which means the value that I might have would be around 1 volt. Okay? But you know, it's a regenerative feedback circuit. It's a positive feedback circuit. Okay? So having this one, okay, so bringing from 0 to 1, it goes through this loop, and that in turn will push to 1.2, and that in turn will push this 0.3 to 0 volt. Okay? Automatically the circuit will perform some regenerative action to pull this one from 1 volt to 1.2, while the other end from 0.3 to 0. Okay? The circuit will perform by itself. Okay? So the only thing is you have to give enough push to perform this operation. Here, so there is some a bistable diagram with potential energy where you have a metastable state, but once you cross that metastable state, you end up having a stable state, and based on that principle we can discuss, but it is out of our portion, so I'll just tell that due to regenerative action, it can get back to these values. Here. So this is our motto. Now, what we do next is to, during this discussion, we have not included this guy. Okay? Now, why this guy is more important to a driver? Because of this input, this driver, this particular transistor will be on, and that in turn will create an additional resistance because of this. Okay? So we have a resistance, and this node is not actually connected to the ground, but rather through this driver, I've been connected to the ground. Okay? So this means I have some resistance followed by which the ground is being connected. Okay? So now, and this voltage is approximately close to the value of 0. It's not equal to 0, but rather it is close to the value of 0. So here is where we have to worry about this WDR. Okay? So it depends only on the WDR to ensure that I try to put this particular node voltage to 0.3. Okay? So this means I need to consider the width of the driver circuit in order to perform this entire write operation. Okay, not just the PMOS and the NMOS, but we also have to consider the write driver circuit as well. Okay, so we have two different variables. Okay, so three variables basically. So I'm going to label this guy the width of the PMOS with WP, while the width of this NMOS is, or the access tensor is defined as PR times WP, while the width of this driver circuit is defined as WDR. Okay, so now I'll just show a set of graph. Don't get panicked. I'll try to explain this. Our goal is to ensure that I could be able to bring this QB from 1.2 volt to all the way to point. Okay, so now we will try to see what are the different combinations of PR and the WDR that I supposed to have in order to bring this node QB from 1.2 to 0.3. Clear? So you have to pull it down. So that this graph doesn't look too much alien to your understanding. Okay. So now here is a set of graphs that I have plotted for PR that is equal to 1 and for PR that is equal to 2 and I think 3. And we are taking some WR ratios. Okay, so this starts with 120 and we will end up with 1440. Okay, which is almost close to 11 times the minimum width. Okay, while a PR of 3 will just have different variations. One will start with 120 and then 360, WDR of 720 and WDR of 1440. Okay, yeah. So now in this case, the first case, you could see that the QB has been dropped close to 0.8. Okay, so the maximum voltage it can be dropped is basically 0.8 when the PR equals to 1. Okay, so this is the first one. Now we'll switch back to WDR that is equal to 1.44 micro. Okay, so in this case, if you look carefully, it is a blue solid line that corresponds to WDR that is equal to 1.44 micro and the PR of 1. So which means any combination of WDR fails to bring this QB well below the value of 0.3. Is that making sense? Okay, so any combination of WDR will not help us to bring this QB below the value of this marked line, which is 3.3. Okay, so all the combinations fails basically. Now we will just take the extreme value where PR equals to 3 and then we will work with first WDR that is equal to 120. Can you find where exactly the graph is? It is this green dotted line, right? So here in this case, again this particular line is a Q bar line which fails to cross this 0.3 desired value. Okay, so this means this particular combination fails. Okay, so we'll just move on to the next one, which is 360. So now in this case, you could see that the dashed line of green one actually crosses this 0.3 for 360 nano for WDR and PR of 3 here. So this passes. Okay, we'll just move on to 720. Now for 720, we have this purple color. Okay, so this is also passes. And for WDR that is equal to 1.44, if PR equals to 1, is a solid purple line that actually crosses. Okay, now we have 3 different options that actually passes our required result. Which one to choose? I will leave a minute for you to think. Which one would be wise to choose? And if you have the answer, please let me know the answer for it. All the 3 actually passes. Right. So which one would actually help us in a better way? We need to find some sweet spot for WDR. So once we find it, then we can use our different procedure to find the value of the exact value of PR that is required. Okay, so let us begin with this first one, where WDR of 360 and PR of 3. One thing that you can feel is that this is my enable input, okay, or the word line that actually switches from 0 to 1.2. So once the word line is enabled, it takes the longest time for us to reach to pull this Q bar well below the value of 0.3, right? But then when I reduce the value to 720, which is this one, okay, how much of the time that is being reduced? Almost like half the time it has been reduced. But then when I try to have this factor, which is WDR of 1.44 micro, this amount is not much. Okay, so if you look carefully, as we double the size, the time to pull this particular Q bar to less than 0.3 is being reduced. Okay, but when I look here, there is a great reduction in the time than compared to the doubling the width from 720 to 1440. The time that is reduced is much smaller. Okay, so this means I have a sweet spot where I can assume that the WDR equals to 720 and I can work. Is that clear? So you might wonder, any of this is giving us the high speed in pulling this Q bar, but the point is that 1440 will also have some other drawbacks. Okay, so which means the data in has to drive a large gate capacitance, which we do not want to have it. Okay, so we have to perform some compromise, which is not being included as a part of your entire experiment because we need a lot of arrays to demonstrate this principle. So in a way, I've just used this method to justify that WDR of 720 is enough for us. Clear? So now that we have found this WDR of 720, now what is left over is to find the value of this PR. Okay, so we have randomly chosen the value of this PR to be higher than the value of 1. Okay, for 1, everything fails. For a PR of 3, one of these structures passes, but then we need to find the exact value of PR. Okay, so what I do next is that once this WDR is being fixed, we'll just fix it here as 720, and then we will perform a parametric analysis only on the PR to find the exact value of PR for which the delta V bar is crossing this 300 millimeter. Clear? So this is what our task is. I hope that it is all clear. If you have any doubt, please ask me. Do you have any doubt?
So first we assume PR is equal to 3, then we find out WDR, again we find out PR.
Yes, because this is being swept in a very coarse manner. Okay, so from 1 to 2 to 3, this is how we sweep it. Okay, but then the exact fine resolution can be done again once we find that the WDR is somehow conclusively you can get this particular result. Okay, so so here in this case we are making some sort of assumptions based on which we are trying to perform. Okay. Any doubt? Basically, his question was like, why did we choose this PR directly as 3, and then why not the other values of WDR? So the point is like it's a design process where you need to consider a lot of permutation and combinations, and in this case, I'm trying to justify that the amount of time it reduces is pretty small when we move from one width to the other width. So that is the first point, and that conclusive result can be derived both for PR that is equal to 2 as well as PR that is equal to 3. So during the simulation, I will try to show with PR that is equal to 2 that there will be a drastic time delay difference from WDR to DR of 360 to 720. But when we move from 720 to 1440, we will not see much of the gain in reducing the pulling power, okay, or the delay to pull this particular Q bar less than 300. Okay, so that I will try to demonstrate. But then this not 2 is not an exact number. So again, we have to perform some iterative process. Yeah, it's like a trial and error, and we do not want this trial and error to happen throughout this entire lab. So that's why we are stuck with 720 with this small justification. Otherwise, in the normal process, you have to perform a trial and error both across PR and WDR to find the optimal sizing for both the cases. Yeah. Yeah. So now, what I do next is to demonstrate both these results. Okay. Okay, underscore read, and this is the schematic that we have. Now, if you look carefully, this is the capacitor that is being taken from analog lab, and here there is an initial condition. Okay, so this one is made. This one will be normally at 0, but we will define it as 1.2. Okay, so that is the very first change. For access transistor, as I said, it's WA, while for the bottom transistor of your inverter, we'll define it as an expression. Okay, so CR with asterisk symbol for multiplication times WA. Okay, so we can also define an expression for the variable. Okay, and that is what we will define. And here we are using a V pulse which has a time period of 100 nanosecond. Okay, so with this setup, let us quickly perform a simulation here. So I'll just try to collect all the variables, and I have also listed some of the initial conditions towards the left side. Okay, so if you want, you can just use this. So in this case, I start with 0.5 for the CR, while WA we are going with 300 nano. So you see, this 300 nano will help us to define a particular value for both the transistors. Okay, so a WA of 300 will define the 300 for this, while CR times WA will define 150 nano for this, okay? But this is not the exact value. What is our intention is to find the relative measure, okay? Not the absolute value finding, clear? So for the transient, I use the same clock period that I've used for the pulse width, okay? And click on moderate, click OK, and next I'll choose all the three signals that are interested. Okay? So one is the bit line, the other one is the Q signal, and the third one is the word line. Here in this case, it has been marked as enable or EN. Okay? So press escape, and you try to perform a run on this analysis. And now here is the waveform where the bit line is being discharged, okay, while this is the enable or the word line that has been activated, and here is your Q signal that has created a bump. Okay. Now to find what is the maximum value of bump that we have created for the default setting, I'm just going to use a calculator for this. So click on Tools, Calculator, and whatever is there in the buffer, please clear. So buffer and the stacks are being cleared. And now choose wave, radio button, go back here and select the Q wave. And then there is a function from the control panel, which is, from the function panel, which is the Y max. To select that Y max, so that in turn will apply the function onto the wave that we have selected. And when you evaluate, it returns us a value that is close to 300 millivolt. Okay. So now our task is to reduce from 300 to all the way to 120. Clear? So what we do next is that we want this expression to be available onto the buffer. Okay, so when I double click from the stack, this expression will get copied onto the buffer. Okay, because it is through this expression we got the value, and we want this expression to be available in the buffer for defining an output expression. Okay, so now what I do next is to collect all the bump maximum values. So due to which I'll try to click on create output setup.
Excuse me, sir. Sir, isn't it supposed to be 600 millivolts? Because in the beginning you told it is 1.
Yeah, it would be 600. Yeah, but because it's a capacitor, it will start while it is trying to rise up. Okay, the voltage across the capacitor keeps losing. So that's why it doesn't reach all the way to 0.6, but rather somewhere in an intermediate value. If it is a constant value like a VDD, when you have a supply voltage, then you can expect to be around 0.6, okay, closer to 0.6. But then because of the voltage is being stored across the capacitor, it starts losing. The moment it is trying to rise up, it also parallelly losing its charges, due to which the voltage across the capacitor keeps dropping, and due to which the maximum rise is not close to 0.6. Yeah, so now when I click on this get expression, whatever is there in the buffer, in this calculator, will get copied. Okay, so I just click on this get expression, and that expression has been copied. Click on add, click OK. So once this is done, we can just get back here to our ADE window. Now whenever we define an output through output setup, how do we get a graph out of it? Can I use this play button that is available in the ADE, or do I need to perform some other analysis? How do I get a graph for this newly defined output expression? Parametric. Okay, yeah. So now among this other three output expressions, I'm not interested in the bit line or in the word line. Okay, so I just want to look at the Q variations, and I want to capture that Q variations or the maximum variations through this expression of Q delta. Okay, now go to Tools, Parametric, and under this variable select CR and change this one from 0.6, and I will just have a maximum value of 3, okay, because I know the value that we will end up having it, so I will not run it till 5 as it is given in the manual. Okay? I will just stop it till 3, and here I am just giving a step size of 0.1, and when I run it, we are trying to increase the value of this NMOS transistor, the pull down transistor. So I'll just change this background color. Windows property, background, change to white, click OK. OK again, yeah. So now the graph on the left side shows the variation of Q bar, the Q bump, okay. So as we increase the value of this CR, the bump height is keep reducing, and that we are capturing through this expression of Q delta. Now what I do next is to place a horizontal line, okay. So, and I place it such that it crosses 120 millimeters. Okay. So this number that we have got is around 2.219. Okay. So what we do next is to round up this value to. So here we finally found the value which is 2.22. Okay. So we will always round it up instead of writing in terms of decimal. We'll just round it up. Okay. So this is the value that we have got it right now. Now we'll just move on to the next one, which is the write operation. Okay. So I can close all of these things. And I'll try to open the write schematic. So here again, apart from this pull up and this access transistor, we also have an extra transistor whose width is being defined to be WDR as the variable. Okay. Now every other setup remains the same. Okay. So even the capacitor will be charged to 1.2 volt with the initial condition setup. Okay. Now just click on launch ADL and copy all the variables from the schematic and define the value of this PR to be 1, and WDR will go with 140 nano and WP as 120.
So it's given 2.4.
140 WB. Correct. The WD 240 nano.
No, sorry, it is 240.
Oh.
Okay. So I'm just following the condition that I've initial conditions that I've put here. Okay. So this again I will run it for 100 nano. Okay. The same period that I have used for the pulsar. And now we'll also collect all the three graphs, the Q bar and the bit line bar, as well as the word line, which is shown as an enabled signal. Okay. So press escape, come back here, and then run it. Okay. So now for the default condition that I've put across this across this WDR and the PR, the graph which is shown in the green color is the Q bar signal, and we could see that it is way away from our 300 millivolt desired value. Okay, so I'll just place one more horizontal line and ensure that this horizontal line is placed at 300. Okay, so it is far away from this 300 millivolt. Okay, now what we do next is to play with both WDR as well as PR to bring this Q bar, which is the green one, well below the value of this horizontal line. Okay, so now in order to perform this, I'm not interested in the bit line bar as well as on the enable signal. Okay, so I'll disable both of these things, and I'll just go to tools, parametric analysis, and I just want to perform a sweep across PR. Okay, so this one varies from 1 to 3, and then I use the linear step. So it was given as 0.5, I guess, in your manual. Please make it as 1 because the simulation will take a long time for us to complete the analysis. So of course, step size is fine. Now in order to add one more analysis in parallel to it, so you can just click on add new row. So this will add a new row for us, where I can select this WDR and change this WDR from 120 nano to 1440 nano. Okay, and the step size is defined as 120 nano. Okay. So with this setup, you just click on this play button and ensure that only the Q bar signal has been selected, because otherwise the graph will look so much polluted. Okay. Yeah. So do not get overwhelmed with the number of graphs that we have. Okay. So first, initially, I'll just place a horizontal line and ensure that it is being placed in such a way that we can find some results from here. Okay. Yeah. So towards the left side, if you just expand this plus button, we end up having two different options. One, the variation of PR. The other one is the variation of this WDR. Now, when I have this PR of 1 and WDR of 120, the graph is way away from the desired horizontal line, right? We will also select the one that has this one. Okay? So even in this case, a PR of 1 with the maximum value of 1440, it couldn't be able to cross this desired result. Okay? Which means the PR of 1 never helps us to bring this Q bar less than 300 millivolt. Is that clear? So now, let me demonstrate the graphs that are more interest to us. So I'll just go with PR of 2 with 120. It doesn't cross. And again, I'll just switch to PR of 2 with 360. So in this case, we could be able to see that it crosses our desired 300 millivolt. Now we will also choose 720 with PR of 2. It again crosses. And finally, what we have is 1440, a PR of 2. Okay? So now, in this case, it is pretty clear that a PR of 2 with WDR of 360 took a very long time for us to discharge. Why? A 720 is quick enough and also could be able to pull it down much faster. But it is a bit slower than compared to 1440. But the thing is, like, it is not too much of difference that I am getting it. Okay, so due to which among these three spots that I have here, which all crosses 300 millivolt target, the sweet spot would be WDR of 720. Is that clear? Any doubt? The only thing is I didn't show the enable signal here. So if you compare, it is the one that we have here is we are not spending too much of area, and we are getting enough pulling down strength as well. Okay, so we'll just go ahead with WDR of 720. So right now, I'll just go back to my ADE and change this to 720, which is the sweet spot. And I'll just go back to this ADE, and I don't want to sweep further the WDR value. Okay. Now, because I know that this PR is stepped, and right now I'll just perform a finer step size tuning between 1 to 2. Okay, because I know that the result falls between this 1 and 2, so I'm not sweeping all the way to 3 as it being given in the manual. So I'll just sweep between 1 and 2. That is enough. Now what I do next is to perform the parametric only on the PR. Okay, so see that I've not enabled this. If you want, you can delete this second row that we have added before, and then we perform only on this. Okay, so before that, we also want to capture the QB minimum, right? So I want an expression to be available in the ADE. So click on this output, setup, and QB min, and I'll just click on this open. Okay, so I need to have an expression. So I'll just play this with the default setting, and then I collect this expression. So clear the buffer and stack, and go to the wave, and select this QB wave. And this time I want to measure the minimum voltage. So I select this Y min. I apply the function of Y min, and when you evaluate, it has to return as a value. It is returning as a value. So, but to define an output expression, I need an expression to be there in the buffer. So double click on the stack expression so that it gets copied onto the buffer. Now you can switch back to this output setup. Probably you might have to redefine this. Click on get expression. So click on add, click OK. So now what I do next is to perform the parametric analysis only on the PR with a final step size of 0.1. And when we do so, we can find the PR ratio. Yeah. So the graph towards the left side I want to place a horizontal line at 300 millivolt. So this in turn will help us to find the PR value. The problem is both the values are overlapping. Okay, do you know any other function that we can use to find the value? Yes, we have already studied about it. Okay, if you don't know, I will perform quickly. Let's see. Okay, so this gives us a value of 1.177. Okay, so that is the PR value that it returns, but we will just make it as a round number, which is 1.2. Okay, so we'll just make it as a round number here. Instead of 177, I may make it as 1.2. Okay, now that we have got almost all the values, but are these values tells us the absolute value of the width that I am supposed to use in my design, or it just gives only the ratio? It returns us only the ratios. Okay, so what I do next is to define some value. Okay, the minimum value that I can use in my design is 120 nano. Okay, so that I am using it. And how will I find this WA, which is the width of our access transistor? How do we find that? PR or CR, which is right. Okay, so PR times WP will give us, so the PR value is 1.12 into 120 nano, and that will, whatever the value that we got is what we need to substitute for the width of our access transistor. Now we also have to find the width of our NMOS transistor or the pull down transistor, which can be written as, how to find the value of this W, D, CR into which W? WA, WP, it's supposed to be WA. Okay? So now this value is 2.22 into whatever the value that you found has to be substituted in order to get the value. Okay? So once these values are done, then we can build the structure, which I will show. So this is the complete schematic of your 60 SRAM. Okay. So now I want you to complete this particular task. The remaining thing you can go through the manual.